are other stars in the universe that vary considerably from our sun. There are stars with over 30 times the sun's mass, and stars with as little as 1/10 the sun's mass. 2/3 of all stars are thought to be in what are called binary star systems, consisting of two stars rotating around one another. How a star appears to us on Earth depends not only on how bright the star is, but also its distance from us. Absolute brightness represents a comparison of how bright stars would be if they were all the same distance from the Earth. The color of a star can help determine its temperature and brightness. The hotter a star is, the more white or blue its color will appear. A cooler star will appear yellow or red. By breaking the light of a star into its component colors by passing it through a device called a spectrometer, astronomers can determine the temperature of the star and which elements it is made of. All stars have a predictable life cycle. All stars are thought to form from the clouds of interstellar matter and gas contained in nebula. According to modern theory, stars are continually forming wherever clouds of gas and dust exist. The typical nebula is 25 light years in diameter and contains enough interstellar matter to make many stars equal in size to our sun. The force of gravity causes the gas, atoms, and dust in the clouds of interstellar matter to slowly be drawn together. As the concentration of interstellar matter in an area increases, so does the temperature. As time goes on, the clouds of interstellar matter begin to glow and are called protostars and will eventually become actual stars. As the contraction continues, the protostars become hotter and brighter. Eventually, the center of the protostar gets hot enough to start a fusion reaction. During fusion, hydrogen atoms unite to form heavier helium atoms. As soon as these fusion reactions begin, the protostar becomes a star. Huge amounts of energy are generated during the fusion process, and the release of energy counterbalances the force of gravity, causing the star to stop contracting. The star is now said to be in a stable state. More massive stars will glow blue and white, while less massive stars glow yellow and orange. A star may stay in a stable state for millions or billions of years, but eventually so much of the core's light atoms are used up in the fusion reactions that the star loses its stability. The center, or core of the star, contracts again, causing it to get so hot that the outer layers of the star begin to expand, enlarging its surface area. The star then radiates more light and appears brighter. In the meanwhile, fusion reactions start occurring in the outer layers. The core has become almost entirely helium from the fusion process. The star expands further, and it becomes a red giant or supergiant. If the star's core gets hot enough, helium atoms fuse in a reaction that forms even heavier atoms. If the temperature continues to rise after the helium is exhausted, heavier elements such as iron will be formed. Depending on its size, the red giant can have one of two fates. It can become a white dwarf or a supernova. If the mass of the main sequence star that formed the red giant is about that of the sun's, it will go on to form a white dwarf. In the final stages of the star's life, with the fuel needed for fusion reactions used up, the temperature and pressure of the core begins to drop to a point where the weight of the star's outer layers can no longer be supported. The giant star collapses on itself, forming a white dwarf roughly the size of the Earth. With most of its fuel gone, the star cannot produce enough heat to remain at high temperatures, but remains hot enough to glow faintly for perhaps a billion years. It will eventually become cold and dark, and is then referred to as a black dwarf. Occasionally, matter from an adjoining star will fall into a white dwarf, causing it to flare briefly, creating a nova. Massive red giants have a somewhat different life cycle. These red giants get much hotter and may explode violently. In such an explosion, a large portion of the red giant's mass is blown away in a large cloud. The mass that remains is crushed to form an incredibly dense core called a neutron star. While this process is occurring, the exploding star flares up into an extremely bright object called a supernova. A supernova may be 1 billion times more luminous than the sun. Hundreds of supernovas have been studied through the use of powerful telescopes that photograph the supernova's activity. Ancient Chinese astronomers documented a supernova in 1054 AD that was so bright it could be seen during the day. The brilliant star faded after about a year, but left behind a great expanding cloud of gas that is today called the Crab Nebula. It is the violent reaction within supernovas that creates all metals heavier than iron in the universe. After the explosion of a supernova, a remnant called a neutron star is left behind. A neutron star consists entirely of electrons. The density of a neutron star is so great that a spoonful of its matter would weigh tons on Earth. These very dense stars spin very rapidly, almost 642 times per second. As neutron stars spin, they shower radiation out in beams like light from a lighthouse. Because they emit pulses of radiation, some neutron stars are called pulsars. Usually, after a few hundred years, the star will stop spinning and no longer emit radiation. More massive star remnants left after the explosion of a supernova form black holes. A black hole is even more dense than a neutron star. Its gravity is so great that even light cannot escape. Astronomers have identified what they believe to be a black hole, Cygnus 11, that has a companion star revolving around it. Matter from the companion star appears to be spiraling into the black hole of Cygnus 11. Astronomers continue to look for other black holes in the universe, seeking clues to their origin. It is hypothesized that the gravitational pull of black holes may be so tremendous that any light coming near them would be trapped by the gravitational force of the black hole. Our understanding of the universe and its beginnings are based on centuries of observation and study by astronomers. But no definitive answers have been reached, and perhaps none ever will, as the study of the universe continues to generate as many questions as answers about its origins and future.